Our first example in this lecture is a design problem. Okay, we're given the following second order circuit where certain parameters are to be determined. Inductance is 1 Henry. This is the input, Vs. And let's label our variables as IL. This is V2, voltage of the second resistor. And let's call this Vc, capacitor voltage, and let's call this current IR1. Okay. Now, the design problem is the following: design the circuit. Okay. Meaning that we have to figure out R1, R2, and the capacitance C, so that the step response for the output V2, voltage of the second resistor, is V2t equals 3/4 plus a first order polynomial where the coefficients are unknown, a plus bt e to the minus 4t volts. Okay, so this is the response for t plus for the second resistor's voltage. Also determine, if possible, the unknowns a and b, the constants. Okay, so the first step is, it seems, to obtain the differential equation. Note that this is, even if you, this is neither parallel nor a series topology, therefore we have to obtain differential equation from the using KCL, KVL, and terminal equations. Okay, so that will be our first step, obtaining the differential equation. First, obtain differential equation. Now, this is the solution V2, and usually we obtain our differential equations in terms of either capacitor voltage or inductor current, but the response or the output of interest is the voltage for the second resistor, so it's neither inductor current nor the capacitor voltage. But still, let's try to obtain the differential equation in terms of the inductor current, because inductor current, in a sense, is very closely related to the second resistor's voltage, because simply V2 equals R2 times IL, because inductor current is also the current of the second resistor. Okay, so therefore it makes sense to try to obtain the differential equation in terms of IL. So let's begin from KCL. 0 equals I R1 plus IC plus I. Okay. So we wrote down the node equation. At this point, IR1 plus IC plus IL must equal 0. So that equals, now, eventually what we want to represent everything in terms of IL. Okay. So let's write what we can write, Vc minus Vs over R1. So instead of IR1, we write Vc minus Vs, okay, so that's plus minus V1, the voltage of the first resistor, divided by resistance R1, plus CdVc, we use the terminal equation for the capacitor current, plus IL. Okay. And then that equals what? We can write the following: 1 over R1 L DIL plus R2 IL minus Vs plus CD L DIL plus R2 IL plus IL equals 0. And to go from this line to that line, what we used is we represented the capacitor voltage in terms of inductor voltage and the voltage of the second resistor, okay, V2. Now, inductor voltage is LDIL, and L is 1 in this case, plus V2. V2 is R2 times IL. Therefore, Vc equals LDIL plus R2 times IL. So we can represent that for Vc in terms of IL and its derivative, which we did here. So what we use is, we use the fact that Vc equals the inductor voltage plus the voltage of the second resistor R2IL. Now, nice thing about this line is that now everything is in terms of the inductor current. So let's reorganize the terms. L C V squared IL plus L over R1 R2 C DIL plus 1 plus R2 over R1 IL minus 1 over R1 Vs equals 0. Okay, for which we can write the following: D squared IL plus 1 over R1C plus R2 over L DIL plus 1 plus R2 over R1 1 over LC IL equals 1 over R1 LC Vs. Okay, so that's our differential equation in terms of inductor current. Okay, next, let's consider a circuit at t equals infinity. Okay, we're talking about step response for positive times. Vs is 1 volt, and then if you wait long enough, the circuit would have reached DC steady state because the only source is DC. At DC steady state, the inductor behaves like a short circuit and the capacitor behaves like an open circuit. Okay, so we can just forget about the capacitor here, and here we just had a line. So what we have is R1 and R2 become in series, and then in that case there will be a voltage division of this voltage between R1 and R2, and some portion of voltage will appear at the terminals of R2. And that portion must be 3 over 4, because as time goes to infinity, this term disappears regardless of what A and B might be, and V2 at infinity equals 3 over 4. And therefore 3 over 4 tells us the ratio of the resistances R1 and R2. So R2 divided by R1 plus R2 must equal 3 over 4. So that's something, some information regarding the parameters of the system. So therefore, let's draw the circuit That's the state at t equals infinity. At t equals infinity, we have 1 volt. Capacitor becomes open circuit. That's steady state. Inductor becomes short circuit. DC steady state. And here we have the voltage that appears across the terminals of our second resistor. This is R1. This is R2. And plus minus this voltage is V2 at DC steady state. Now what's V2 infinity? We look at the solution, the step response, plug in t equals infinity and this term disappears. What we're left with is 3 over 4. Therefore, here we have 3 over 4 and by voltage division that must equal R2 over R1 plus R2. And that tells us that R2 must be 3 times R1. Okay, this is equals 3 over 4 volt. Therefore, R2 over R1 plus R2 equals 3 over 4, which yields R2 equals 3 times R1. Okay, so this is the first piece of information that we gather from the circuit and the step response. Now, what's the characteristic polynomial? Characteristic polynomial is obtained by looking at the left-hand side of the differential equation, and characteristic polynomial is independent of the formulation variable. Okay. So we formulated in terms of IL. You could have formulated in terms of VC. Still, we would have the same characteristic polynomial. Anyways, the characteristic polynomial is s squared plus this times s plus that coefficient. What we know is we're given that L equals 1 Henry and also R2 equals 3R1. Okay? Plugging in those information, we can write V of S equals S squared plus 1 over R1C plus 3R1 because L is 1 and R2 is 3R1. S plus, okay, this ratio is what? 3 plus 1 is 4, L is 1, so what we have for the zero for the terms coefficient is 4 over C. 4 over C, so that's our characteristic polynomial. Okay. Now, what we know about the characteristic polynomial, remember that the solution V2t was some constant plus first order polynomial a plus bt times e to the minus 4t. So when we have, so clearly that constant is a particular solution coming from the input, and the other part is a homogeneous solution. Okay, a plus bt times e to the minus 4t. So homogeneous solution is first order polynomial times some exponential. That tells us that the natural frequencies of the circuit must be repeated. Repeated at where? We look at the exponent. It's e to the minus 40, therefore they're repeated at the location minus 4. So that means characteristic polynomial must be s plus 4 times s plus 4, because both natural frequencies are at minus 4. Hence, this must equal s plus 4 squared. Okay? This information we gather directly by looking at the step response, or the homogeneous part of the step response. Now, if you write this in open form, what you have is s squared plus 8s plus 16. Okay? Hence, this must be 8. And here, this must be 16. This being 16 tells us that C must be 1 over 4 farads. So we obtained C. And then this equals, at that point we will have known C, and then this equals 8 will tell us what R1 should be. And once we know R1, we immediately know what R2 is. Okay, so let's continue. We have figured out that C equals 1/4 farads, and this is 1/4 now. 4 over R1 plus 3 R1 must equal 8. Okay, so that characteristic polynomial is S plus 4 squared. So that leads to 3R1 squared minus 8R1 plus 4. Therefore, R1 is determined through this quadratic equation. Let's figure out the roots of this quadratic equation. This can be written as 3R1 minus 2. Then we have R1 minus 2. That equals 0. Okay, so there are two possibilities so that this equation is satisfied, or this gives us 8. It's either R1 is 2/3 or it equals 2 ohms. That means we have a non-unique solution. So R1 equals 3 ohms, which implies R2 equals 3 times that, 2 ohms. Okay, so that's a possibility that realizes the design criteria. The other possibility is R1 equals 2 ohms and R2 equals 3 times 2, 6 ohms. Okay. So either this pair or this pair will satisfy the design requirements. Okay, so the design of the problem is complete. Let's also figure out if we can the coefficients of the first order polynomial that appears in the step response. Okay, so that's our next problem. So what we have is V2 of t equals 3/4 plus A plus Vt e to the minus 4t volts. Okay. So the question now is, what are A and B? Now this is step response. Therefore, by definition, we're talking about a zero state situation, and that means IL 0 equals 0 and VC 0 equals 0. Okay. Now, the solution is in terms of, well, neither IL nor VC, so we have to, therefore, transform this information into the initial condition information for V2T. Okay. So what's V20? V2 was the voltage of the second resistor, and therefore it's R2 times the current of the second resistor, and the current of the second resistor is same as the inductor current because they're in series connection. So this is R2 times IL0. Since initial inductor current is 0, that means initial voltage for the second resistor must be 0. And how about dV20? So this is R2 DIL 0, and that's R2 L VL 0. Okay, because DIL is VL over L, and then we can write VL as what? VC minus V2, and V2 is R2 times IL. So what we have is VC0 minus R2 IL0. Since VC0 and IL0, they are 0 by definition of zero state or step response, hence dV20 must also be 0. Okay. Now we have two constraints, V20 equals 0 and dV20 equals 0, and by applying those two constraints to the solution, we figure out, hopefully, the unknowns A and B. Now, V20 equals 0 implies plugging t equals 0. What we have is this term disappears, bt term. What we have is a here, this is 1 and this is 3 over 4. A plus 3 over 4 equals 0, and that gives us a. Okay, so a must be minus 3 over 4. And dV20 is also 0. Therefore, differentiate this and plug in t equals 0. In that case, we have minus 4a plus b equals 0. That means b has to be minus 3. Okay. So by using the initial condition constraints, we were able to compute these two unknowns, a and b, in the step response. In our next example, we have no source, but we have a switch that changes position, which readjusts certain initial conditions, which we have to figure out. So this is the case that we're going to be studying now. We have capacitor here. Capacitor. Initially switches in that position, and at t equals 6 seconds, switch moves from this location to that location. Okay. The initial conditions are given as V1 0 is 18 ohms, V2 0 equals minus 10 times E ohms, somewhere around minus 27, and IL0 is minus 2 amps initially. And the question is V2t. We have to figure out the solution. V2t for t positive. Okay. Now, initially, it switches in that location, so that tells us the following. First of all, the current here is 0 because this is open circuit. The current through the capacitor 0. That means rate of change of voltage is 0. That means voltage remains V1 constant until the switch changes position. What else? IL is short circuited initially. Okay. Now okay, so that means that's a dual situation. VL is L, DIL. Okay, so DIL is VL over L. VL is 0 because short circuit. That means DIL is 0. Rate of change of current for inductor is 0. So that means inductor is not changing. Inductor current is not changing. It's also constant until the switch changes position. What's not constant is capacitor, the charge in the second capacitor, because it's connected in parallel or series with this 2 ohm resistor, and that makes the first order circuit as far as the second capacitor is concerned. Okay, so for a while, until t equals 6 seconds, this capacitor, the charging this capacitor is discharging through that 2 ohm resistor. Okay, so let's write our observations down. Okay. From 0 to t equals 6 minus, just before the switch changes position, what we have is C dV1 equals I1. C is 1, therefore dV1 equals I1. This is I1 and it's 0 because that's open circuit for a while. So that means V1T equals V1 0 until switch changes position. T equals DIL equals 1 over L times VL. This is short circuit, therefore VL is 0. That means VIL is 0. That means IL is constant. ILT must equal IL 0. Okay. Until the switch changes position. And how about our third dynamic component? Second capacitor, dV2 equals 1 over C I2. Okay. That equals 1 over 3. Okay, so this is I2. This is open circuit. There is no current, therefore we can forget about this branch here. This I2 flows over the resistor in that direction. Okay. So this is V2, therefore this is V2. V2 over 2 is resistor current in that direction. Therefore I2 must be minus the resistor current. Resistor current is V2 over 2. Therefore minus, that is minus V2 over 2. Hence we have dV2 plus 1/6 V2 equals 0. So that's the first order differential equation, homogeneous. Therefore the solution is the initial condition times e to the natural frequency times t. Initial condition is minus 27. Therefore V2t equals minus 10e times e to the minus t over 6 volts. Okay, so since we were asked for V2t, we figured out what the second capacitor's voltage is initially. So 4 times between 0 and 6. Now what happens at t equals 6 seconds is the switch changes position, and that by KVL or maybe KCL forces certain voltages and currents perhaps to jump. Okay. So let's see what happens then. So we have to make this analysis throughout this infinitesimally tiny interval. T equals 6, from t equals 6 minus to t equals 6 plus. 6 plus. So here we have the circuit. This is IL, and this goes to IL. Okay, when the switch changes to that location, what happens is this capacitor and that capacitor, they become in parallel, and this capacitor, the inductor current, the inductor and the resistor, they make a loop. Okay. So this here is V1, 1F. This is 3F. This current is I1, this current is I2, and by KCL, sum of those three currents equals 0. Now what we know about IL, and we will use that information, is that it's bounded. Because by our assumption, inductor currents and capacitor voltages are bounded. And using that information, now we will be able to figure out how the capacitor voltages readjust themselves when the switch changes position. Okay, so for that, let's write the terminal equations. V1 6 plus the value of V1, voltage V1, at t equals 6 plus equals V1 6 minus, which we know is AT, plus 1 over the capacitance, so 1 over 1 for this case, from 6 minus to 6 plus I1 t dt. I1 is the first capacitor's current. Okay. Then let's do the same thing for the second capacitor, V2 6 minus plus 1 over the capacitance, 3 from 6 minus to 6 plus I2 t dt. Okay. Now let's re-express I2 in terms of other currents. So that equals V2 6 minus plus 1/3 6 minus to 6 plus. By KCL, we have minus I1 t minus IL t dt. And IL t is bounded because it's inductor current. And since it's bounded, we can ignore it because integration is through an infinitesimally tiny length of interval. So we can write 6 minus 1/3 I1 t dt. Okay. So V1 6 plus equals V2 6 plus. When the switch changes position, it forces V1 and V2, or capacitor 1 and capacitor 2, to become parallel. And by KVL, those two voltages must equal one another. Therefore, we can write 6 minus to 6 plus I1 t dt equals. Okay. From the first equation, that equals this minus V1 6 minus, and V1 6 plus is V2 6 plus. Therefore, we can write V2 6 plus minus V1 6 minus. Okay. And then, using the second equation, this time this integral can also be written as what? V2 6 minus V2 6 plus times 3. Okay, so that also equals 3 times V2 6 minus V2 6 plus. Okay. And therefore, in this equation, V1 6 minus is known, it's 18. V2 6 minus can be computed because we know what V2t is before the switch changes position. This is known, this is known. The only unknown is V2 6 plus. And that we can write as V1 6 minus plus 3 V2 6 minus divided by the sum of capacitances, which is 1 plus 3, 4. That equals, this is 18 plus 3 times minus 10 e times e to the minus t over 6 evaluated at t equals 6. So we have 6 over 6. Okay, so this makes e to the minus 1. Here we have another e, and they cancel one another. What we have here is minus 10 times 3 minus 30 plus 18. minus 12 divided by 4 minus 3. Okay, so that is minus 3 volts. Okay. We also have to figure out IL6 plus. And IL6 plus is IL6 minus because the voltage of the inductor has to be bound. Okay, so it makes a series RLC circuit with the capacitor and the resistor. Okay. Also, IL6 plus must equal IL6 minus, and we know IL6 minus that equals minus 2A because IL was constant for times between 0 and 6 minus. Okay. Now, with the initial condition of the inductor and the second capacitor, we can deal with the case for t larger than 6. When the switch changes position, this is the situation that we have. Okay. This is 3 Henry, 2 ohms, so that's the direction of IL. Now we have E2 for this capacitor. Now the question is, what's that capacitance? We had 3 farads, and then that was parallel to a 1 farad capacitor, first capacitor. Therefore, we can replace those 2 capacitors with a single capacitor. The capacitance is the sum of individual capacitances for F1 plus 3. Okay. Now for this series RLC circuit, we know IL6 plus, which is minus 2 amps, and we know V2 6 plus, we just computed it, it's minus 3 volts. Okay. Therefore, we're now ready, because we have everything we need, to write down the solution. So the differential equation is dV2 plus 1 over LC V2 equals 0. The right hand side is 0 because we have no source in the circuit. And for the parameter values given, 3 Henry, 4 farads, and 2 ohms, this differential equation becomes plus 2/3 dV2 plus 1/12 V2 equals 0. Okay, we need the initial conditions, that is V2 at 6 plus and dV2 at 6 plus. Okay, so V2 at 6 is minus 3 volts, so that's what we computed. And dV2 at time 6th second equals what? IC 6 over 4 by terminal equation. Okay, dV2 equals dVC equals IC over C, and this is the current IC, which is minus IL. Okay, therefore that equals minus IL at 6 over 4, and IL6 is minus 2 amps. Therefore, that yields 1/2 volts per second for V2 dot at t equals 6. Okay. Now, by looking at the differential equation, we gather the characteristic polynomial from which we obtain natural frequencies, and those natural frequencies will tell us the following, the homogeneous solution. And by applying the initial condition constraints to the homogeneous solution, we figure out the response. So the the characteristic polynomial for this circuit is, look at the differential equation, pick the coefficients from the differential equation. We have s squared plus 2/3 s plus 1/12. This can be factored into s plus 1/2 and s plus 1/6. Hence, the roots are at minus 1/2 and minus 1/6, both negative and real, distinct, meaning that we're talking about the overdamped case. S12 equals minus 1/2 minus 1/6. Remember that in the previous example, in our design problem, we had both roots at -4. When we have such repeated root situation, we call that case the critically damped case. Okay. This is all. Now we know the form of the solution. E2t equals some constant times e to the first natural frequency times t plus some other constant times e to the second natural frequency 6. Okay. Now for ease in our computations, it's better to write, of course, in that case, this K1 and K2 will be K1 tilde and K2 tilde, because now we're talking about the initial condition, t equals 6. It's easier to work with if you write t minus 6 over 2 and t minus 6 over 6 here. Now, let's figure out K1 and K2. For that, you can use initial condition constraints. V2 6 equals minus 3 implies plugging t equals 6, and what we have is K1 plus K2 equals minus 3. So that's our first equation. Then differentiate V2 and then plug in t equals 6. In that case, you obtain minus 1/2 K1 minus 1/6 K2. That must equal dV26, which is 1/2 volt per second. Two equations, two unknowns, from which we obtain K1 must be 0 and K2 must be minus 3. Therefore, V2t equals minus 3 e to the minus t minus 6 over 6 volts. Okay. For t positive. Okay. And for t negative, we have what? We had minus 10e times e to the minus t over 6. Therefore, we can combine those two pieces and sketch the response. Okay, we'll get a better understanding of what's going on. Okay, t seconds e2t volts. So initially we read minus 10e, so that's given. We're somewhere here, minus 10e. E is 2.71828, so it's about minus 27. And until t equals 6, what's happening is we're decaying towards 0 with a time constant of 6. Something like this. towards 0. At t equals 6 minus, let's say, we reach minus 10 volts. V2 becomes minus 10 volts. Okay. And then at that instant, switch changes location, forces the two capacitors to become parallel. That means by KVR forces their voltages to become equal, and that results in a drop of 7 volts for the second voltage capacitor. Okay. So we drop to minus 3 from minus 10. And then from that point on, we keep decaying with time constant of 6 again. And what we're heading toward is towards 0. Okay, so the overall response, more or less, looks like that.